All right, welcome back to the Aspire 101 or Electrified Transportation Systems course in Aspire. And welcome to everyone who's able to join. And today we look forward to a discussion and presentation by one of our leading experts in battery systems and battery management systems and control and all their implications for electric vehicles in particular. So Professor Scott Trimboli will be presenting for us today. As usual, we encourage discussion and Q&A, and I know, Dragon, I don't know if we've gotten anyone to drop off of video mute yet to ask a question, but feel free if anyone would like to drop off video mute and raise their hand directly. We'll be watching the chat, and Scott will just interject if we see a question in the chat as we go.
Great.
But again, feel free to drop off of at least your voice mute and ask questions throughout. And we look forward to an engaging discussion. At the end of the time, we might just make a couple of comments, checking in on final projects and how we're progressing and the deadlines coming up in April. But for now, Professor Trimboli, I'll turn it over to you.
All right. Thank you, Regan. I'm going to go ahead and share my screen and get started here. So hopefully you can see soon a PowerPoint. There, does that look acceptable?
That does. Yep, full screen.
All right. Okay, good. Well, thank you everybody who made time out of your day to attend this lecture this afternoon. My name is Scott Trimboli, as Regan mentioned. I'm an associate professor of electrical and computer engineering here at the University of Colorado, Colorado Springs. Where my specialty is actually control systems and control theory. That is where I grew up in my educational and research realm. Over the last, we're going on about 15 years, I've been applying that knowledge in the area of lithium-ion batteries, and in particular, battery management. And I work here at UCCS with my colleague, Greg Plett, who some of you may know from a series of well-received textbooks he's written on the topic, and we mutually conduct or jointly conduct this research. And he and I have put together this presentation to give you an introduction to the realm of battery management as it applies to electric vehicles. This is a very topical topic, if you will, for this lecture. We integrate into the overall Aspire scheme on the receiving end of a lot of the charging infrastructure that we talk about in Aspire. There are other factions or other projects in Aspire working on roadway electrification, charging stations, and charging electronics and hardware. We look at the other end. What happens when that charge is introduced into a battery cell? How can we manage the introduction of that charge into the battery cell in a safe and efficient and effective way so that our batteries last a long time, they stay healthy, and perform at the maximum of their capabilities? So that's sort of the top end ideas that we examine here in our research project. So what I'm going to talk about today, I'm going to talk about two aspects. Battery cell modeling, in other words, representing battery cells using mathematical representations and giving you a little bit of understanding of how the battery works and how we go about mimicking its behavior. And then how we use those models. In part two, I'm going to talk about some algorithms. I'll just give you a sampling of algorithms that we use for battery management that leverage the models that we'll develop. So the purposes of battery management are illustrated here. Of course, a lithium-ion battery, as you all well know, is pervasive now in our lives. It powers our phones, our laptops, and even our electric vehicles today. Why? Because lithium-ion batteries have a very high, what we call energy density, right? We get a lot of energy stored in a very small package with a reasonably lightweight configuration, although you would consider nothing really light about a lithium-ion battery. But whenever you put a lot of energy into a small package, you got to be very careful, right? We have to be very judicious with how we introduce current or extract power from this battery cell. And that's the role of the battery management system, to ensure we can operate our vehicles safely, that we can detect when it's operating out of that safe realm, and then hopefully take some actions to mitigate any problems that might occur. We want to protect cells from damage, right? Abuse, failure cases, right? We don't want one of those catastrophic battery fires to occur. And more importantly, for those of us like me who drive an electric vehicle, we'd like those batteries to last a long time, right? We don't want them to go off that performance cliff we often see in all too often in our cell phones. We want to maintain the battery pack in a healthy state where it can fulfill all of its functional design requirements, right? I want to be very careful when I'm driving that car and I hit up on a hill, or I want to get around that truck. I want to have that boost of power available from my battery at that moment so I can operate well in traffic. And then prolong the life of the battery under normal operating conditions, right? I want to let my overarching vehicle controller to know what are the best operating strategies for my battery as we move through our operating regime. We accomplish these objectives by something called the battery management system. And what we see in the picture there is actually a project we did here in the predecessor to Aspire back about almost 10 years ago now, where you're looking at boards which actually perform some battery management functions that are assembled on top of a battery pack. That particular one is a quarter pack for a Ford C-Max car. And each module is interacting with a number of cells underneath, and both monitoring and measuring the status of that battery cell and modifying the way we interact with that cell with respect to current. So the basic functions of a battery management system are, as mentioned, to make physical measurements of what we are able to measure in a battery cell. And it turns out we can't measure very much. We can measure the voltage across the terminals. We can measure the current that we push in and out of a battery cell, and we can measure the temperature, usually at the surface of the battery cell. Unfortunately, there's a lot of other attributes to the cell that we'd like to know that are kind of buried into the electrochemical behavior of the battery. And I'll talk about that a little bit later. But nonetheless, these are really the only things I can conveniently and economically measure. And so that's what my battery management system has to work with. So given those signals, we develop algorithms, right? Computer programs that do a number of things. The most important, and the one with which most of us are familiar, is the state of charge, right? We want to know at any particular moment in time, how much is left in my battery, in my phone? Is it 80%? Is it 20%? Or, or worse? State of health. This was a little bit more esoteric, right? I want to know over time, how is my battery pack holding up, right? Does it still have the capacity and the performance it had when I bought it? Probably not, right? Batteries degrade over time. And can we reduce a measure, a sensible measure of that as time goes by? Another function is to perform what we call balancing of the battery pack. And if you look at the notional picture up at the top there, those batteries are showing different levels of energy content. It turns out that a battery pack, for a variety of reasons, operates better, more effectively, more efficiently when all of those levels are about the same. But they get out of kilter over operational life of the battery, and periodically we have to bring them back into alignment. This is a function of the battery management system called balancing. And then finally, I mentioned here, we wish to compute the available energy, which is related to the state of charge. I'll talk about these later. And then something very important called the state of power, very different from the state of charge. Whereas the state of charge tells me how much energy resides in the pack, the state of power governs how quickly I can extract that energy out of that battery pack. It's a very different idea, but very important for any battery management system to keep track of. Of course, our algorithms that we build to perform these functions rely almost entirely on mathematical equations, on mathematical representations or models that can describe our underlying battery cell operation. So I'm going to talk about some of those models here in part one, just kind of give you a flavor without delving into too many of the details. The basic taxonomy we can view for a battery cell model falls into these two categories. The equivalent circuit models, or what I call the empirical models, and the physics-based models. Equivalent circuit models, or the empirical models, are models that are constructed to essentially mimic the input-output behavior that we observe from a battery using, in this case, common circuit elements. So it turns out that I can, if I cleverly construct a circuit out of resistors, capacitors, and other electronic elements, I can reproduce almost the same input-output behavior that I can get from an actual battery cell. And it turns out these are extremely useful. They are simple to understand, simple to implement, and they are pervasive in battery technology today. No doubt, the phone that you have in your possession right now has this underlying model that is governing its state of charge and other algorithms. The model that you see there, as you can see, there's resistors, capacitors, so the and a state of charge dependent voltage source. And these, of course, are, as I mentioned, cleverly designed to represent processes that we know occur inside of a battery. For example, a battery cell exhibits an ohmic resistance. That's the R0 that you see in the right, on the upper right of that top diagram. So if I pass current through a battery, the first thing that happens, I get an instantaneous voltage drop because of all the substance and the materials that comprise the battery cell. But there's also, at a lower level inside the battery, there are diffusion processes, both solid and liquid diffusion, as ions migrate through the battery structure. And these can be accurately mimicked by an RC pair, right? A first order response. On the left, the dependent voltage source is what we call our open circuit voltage. When a battery is resting at a complete equilibrium and I measure voltage across the terminals, I'm measuring the open circuit voltage. It's in the most quiescent state. Turns out the open circuit voltage is a direct function of the battery state of charge. It will be lower when I have a small state of charge, a very low state of charge, and the voltage will be higher when I have a high state of charge. And it's in fact that relationship that gives us the information we need to make accurate state of charge estimations for your battery. Although good, from an input-output perspective, the equivalent circuit model doesn't really give me any insight as to what's going on deep inside the battery. For that, I need to turn to a physics-based model. And there you see a representation on the bottom. Now, a battery cell electrode, and what I have there is a cross-section of an electrode that is basically a sandwich configuration with a current collector on the left side, a current collector on the right side, that sandwich a negative electrode and a positive electrode separated by a non-conducting separator material. The way the battery works is these electrodes are of a porous nature and they comprise an amalgam of particles. Those particles can house lithium ions. So the ions migrate from one side of the cell to the other, depending upon whether I'm charging or discharging. The migration of those ions sets up a current flow that will close as I connect the current collector or the outer terminals of the battery to a load in the external circuit. These models are very informative. They are built from first principles of physics. They enforce our conservation of mass, conservation of charge. They capture the reaction kinetics of all of the reactions going on. And if I model this very carefully using those ugly looking equations in the bottom, I can really simulate everything going on inside the cell that is of importance to us. So I'll show you some of the benefits and trade-offs between using these two models as we move forward. So diving a little bit deeper into equivalent circuit models, so I'll just kind of breeze through some of this. Like I mentioned, models are sets of equations that describe something for us. We can build these up using the simplest of circuit elements. In fact, the simplest battery cell model I can build is that one in the lower right. All I have is an open circuit voltage source, period. And I ignore everything else, right? If I want the most simplistic battery cell, that's it. Is it accurate? No, not really. It might serve the purpose for some applications, but it does win on simplicity. The equivalent circuit models that we can build up in increasing complexity, as stated, give us a feel for how cells respond under different usage scenarios. And as I mentioned, they're used pervasively in industry. So this model is oversimplified, but it provides a good starting point if we want to sort of add complexity and layers to this model to see how we can better capture the actual behavior of a battery cell. So batteries, fundamentally, what do? They supply voltage to a load. Well, that's what that model is showing me. So at the ground level, it's obviously accurate from that standpoint. So an ideal voltage source will be part of our equivalent circuit model. Let me talk a minute about state of charge and capacity. These are two very important parameters that we use to describe the state of a battery. So when a battery is fully charged, as I mentioned before, the open circuit voltage is higher than when it's at a low state of charge. So if we can put a dependence on a cell's state of charge, we can improve the accuracy of our model. So we can take that simplified model from the previous slide where I had just had a fixed voltage source, and now I insert this state of charge dependent voltage source. And I can define now when my state of charge, which we denote by Z here, is 100%, my cell is fully charged. The OCV is at the highest value. When it is at 0, my cell is fully discharged, and that's by definition, and my voltage is at its lowest allowable level. We also define capacity, and we usually use the term Q for capacity as a measure of the total amount of charge that's removed when I discharge from 100% down to 0%. In other words, the total amount of coulombs that were extracted from that battery as I effected that discharge. So based on that sort of simplified understanding, if I look at the lower left, I can model my SOC simply by a first order differential equation, right? Z dot is equal to the negative of the current divided by the capacity, right? Coulombs per second over coulombs, and I have coulombs per second on Z dot. My voltage then is represented by my OCV at the stipulated state of charge. I can convert all of this into discrete time, and we do that very commonly because all of our simulations for battery management systems will be executed digitally. One aspect that we must consider is that when I charge and discharge a battery, all of the charge that I insert or all of the charge that I extract is not done with 100% efficiency. And we can model this by including what we call a coulombic efficiency factor. We call that eta. It's some number a little bit less than 1. It's usually in the 0.995, 98, 99 region. And it can be defined differently upon charge or a discharge. So now we have a battery with a SOC-dependent voltage source. And I'm going to talk now about polarization. So we have some voltages that set up in the battery as current begins to move through it, as I alluded to earlier. Polarization, of course, is the difference between the terminal voltage and the open circuit voltage due to the passage of current. In other words, I'm no longer at an equilibrium state, so I have some adjustments to make to the OCV to get that voltage I measure at the terminals. So we know that a cell's voltage, for example, drops when the cell's under load. I can model that very simply by putting a resistor in series with the ideal voltage source. So I can now improve my voltage calculation from OCV to OCV now offset by RI or IT, not in this case. The voltage is greater than OCV on charge, right? It jumps ahead of it, and it will be less than OCV on discharge by virtue of the direction of the current. So R naught in this case models what we call instantaneous or ohmic voltage change due to a current step. However, it turns out that if I exercise a battery in the lab, I see in addition to this ohmic drop, which is that instantaneous drop off that you see right at the edge of the step in the diagram below. In addition to that, I see this dynamic first order curve that shows up as well. Well, that's a portion of the dynamic response. That's one that evolves over time due to the current step. That is physically due to diffusion processes in the cell. And so for that reason, we call it the diffusion voltage. We can represent that diffusion voltage by an RC pair that we put in series with the ohmic resistance R naught. So now what we have is something that is commonly referred to in the literature as the Thevenin model. And the Thevenin model is actually quite good. And with proper identification of the parameters, the R's and the C, and proper identification of the OCV curve, we can come up with a very reliable and realistic input-output behavior characteristic for our battery cell. In order to improve accuracy even further, we can add more RC pairs, because as it turns out in reality, the diffusion processes inside the cell are actually spread over different time constant regimes, and these are sometimes better captured by adding several more RC pairs. Of course, every time I do this, I'm adding to the complexity of my model, and I often have an interest in trading off additional accuracy with mitigating the growth of complexity. One other improvement we can make is to recognize that many battery cells exhibit what we call voltage hysteresis. And that is that I'm going to have a voltage change that will vary depending on whether I'm charging or discharge. And that's in addition to the two polarization voltages that I just talked about. And so we can add a further nonlinear hysteresis element to further capture that behavior in cells that exhibit hysteresis. And here's an example of how that hysteresis might look. And you can see the difference for some of these cells. I'm charging this cell, right? And I'm coming up along this line. And if I discharge, I fall along the bottom line, right? So there's quite a bit of difference in here. And now you can imagine if I have a battery management system that's trying to estimate state of charge, right, down here on the horizontal axis, from some kind of a measurement of voltage, I better know which way I'm moving, or I'm going to have a lot of uncertainty in my SOC estimate based on hysteresis. Turns out some cells exhibit much more hysteresis than others. LFP is one chemistry, iron phosphate, that exhibits quite a bit of hysteresis. And that's exhibited in this kind of a fashion here. Some of the more common cells used in cars, the NMC, nickel, manganese, cobalt cells, exhibit very little hysteresis, so this is less of a problem there. We have developed in-house a first-order model of hysteresis, a nonlinear model that does a very good job at capturing this effect. So we put all this together, and we utilize in our studies here what we call the enhanced self-correcting, or ESC model. So that has all the good stuff in it. We've got the series resistance, we've got sets of RC pairs, we have a first order nonlinear hysteresis element, and an accurate OCV model. The nice thing about this model is that we can describe it in a very convenient, discretized, in this case, state space formulation. Where here my states are, this is for a single RC pair. My state of charge is Z. IR is the current across my RC pair, assuming I have one of those, and H is my hysteresis state. More RC pairs will add more IR states to this state vector. So I have a 3x3 state matrix, and then some, you see some nonlinear aspects to this model. And then I build the output voltage, as we already discussed. I've got my open circuit voltage dependent on the SOC. I've got my polarization, diffusion polarization from the RI, got my ohmic offset, and then MH is the hysteresis effect.
Professor, I have a question.
Yeah, go.
How many RC pairs do you typically use? Do you get diminishing returns, or after a couple, then do you get no returns after a while, or what?
Yeah, that's a great question. Yeah, so to be honest with you, you can get excellent model performance with one RC pair. Two RC pairs does improve upon things. We find if you go much beyond two, you're complexifying your model, and you're getting very diminishing returns beyond there. So in practice, unless we're after something that's ultra precise, us being engineers looking for a good enough solution, see that about a 2 RC pair ESC model is excellent at representing the performance.
Right, okay. And if does having two versus one RC pair, does that double the complexity of your equations or increase it by 10 or 20 or 500%? What does that do to your
Yeah,
equation?
just think of it in terms of matrix multiplies, right? So I have a matrix that is n, right? And so there are n squared multiplications going on there, and I want n to be as small as possible to minimize the number of adds and multiplies and adds that I have to perform for a matrix multiply. And so those grow, as you know, with the square.
Right. Okay. Yeah, that makes sense. Thank you very much.
All right. So once we have this model identified, it's not any good unless we can accurately identify the parameters. And a big part of our research goes into that aspect of this field. So probably at the most fundamental level is characterizing cell open circuit voltage. And there's a series of very carefully scheduled tests that we perform that involve slow discharges and slow charges, and then letting the battery come to a quiescent state, then measuring the voltage at each of these state of charges. So we have a very carefully defined protocol that we use. It turns out that when you charge and discharge, you get slightly offset curves. Part of that's due to hysteresis. So we have to somehow combine that information in an interpolative way in order to get a single OCV curve that most accurately represents things. And so we have those built as well. And here's an example of that. So here's the discharge in the upper right curve. The discharge voltage might be the blue curve, the charge voltage, the red one, and then the actual OCV is the black dashed line in between them that's obtained using various interpolation techniques. And so part of that offset is really due to the fact that when I'm doing my charge discharge test, I'm moving the current. So I'm getting polarization voltages in there. And so they're, as I mentioned, they're going to be higher on charge, lower on discharge, and they're going to separate those curves. But we have to kind of suss out where the real OCV lies between those. And we have developed many methods to do that very accurately. We find the OCV is also, in a sense, temperature dependent. And so we have ways of regressing temperature dependency into an adjustment to our curve formulations as well. So the way we use this in our model is usually by table lookup. So we have interpolated table lookups in order to calculate the OCV for a given state of charge. Other people use, they fit various order polynomials to these curves, and they can do a function evaluation. The rest of the parameters are best evaluated using what we call dynamic testing. So at various temperatures, we run the cell through these prescribed dynamic protocols. The one you see on the right, upper right, is a drive sequence that's well known in the industry. It's a very repeatable sequence that exercises a lot of dynamic energy movement within the cell. And what we do is we do that, we run that through our model, we run it through an actual cell, and then we do basically a parameter optimization in order to hone in on what the correct R and C values are that match the voltage performance the best. And so that's our dynamic process. So in this particular case, what you're seeing here now is the model, the resultant model is in red superimposed on the blue output. That's a voltage you're seeing now in the upper right. And the lower left is a close-up of that voltage over a very small time window. So you can see the accuracy, the efficacy of this model when used in this dynamic realm. All right, so ESC models, the equivalent circuit, or the equivalent circuit or empirical models, we've talked about, great at input-output. Also, they are computationally the simplest, and another term we like to use, they are conceptually the simplest. And that there's a big part of that that's important in this industry. It's very difficult sometimes to get people to accept solutions that may be better for their problem when they don't conceptually understand them very well. And you run into that issue with physics-based models. If we want to understand really what's going on with respect to cell aging in particular, we have to keep track of electrochemical-based quantities. And some of those quantities here, not to give you a big tutorial on battery chemistry, but we have things like the potential, right? The voltage potential in the solid material of the electrode. There's a separate potential measured in the liquid electrolyte. There is a quantity of lithium, the concentration of lithium in the solid material, the concentration of lithium in the electrolyte material. And then, of course, we have the rate of lithium movement between the different phases. So all of these parameters kind of come together in these physics-based equations to dynamically describe what's happening inside the cell. Of course, models, we can develop them at all length scales, all the way from the atomic, the molecular, to continuum scales. We use continuum scale models because we can run them in real time on desktop PCs, and they are amenable to embedded applications that are required for battery management system applications. So here's the kind of a closer look at the continuum scale P2D model equations to make your head hurt or your eyes bleed. But these are, these are a set of coupled partial differential equations. There's an algebraic term there at the bottom, the Jn, that's the reaction rate, the Butler-Volmer equation. The others are spherical diffusion in the assumed spherical particles, as well as linear diffusion through the liquid electrolyte. So all these, as I mentioned, all these equations couple together and simulate our cell. The parameters that are highlighted in red are parameters that we need to keep track of in order to simulate the model. Here's an example of diffusion. That's the underlying process, right, that actually drives the cell dynamics. And most of the equations kind of boil down to diffusion equations of the form shown at the top. And here's a very nice little numeric simulation of sort of a discretized solution example done using a discrete Euler forward rule. And you can see the result of a process diffusing through in this case, a solid material. Well, open circuit voltage was very important for the ECM. It's equally important for the physics-based model, or what we call the PBM. Some cell level variables can be understood easily from them. The OCP capacity and SOC kind of come out rather naturally from this set of equations. As we already talked about, OCV is defined in the exact same way for this set of equations for the physics-based model. But we have different meanings when we talk about equilibrium, because now we can start talking about these concentrations, the concentration in the solid of lithium, the concentration in the electrolyte. These become uniform. They become flat lines when I'm at equilibrium. So that helps me to set some of the initial conditions that are necessary for simulating this physics-based model. So these are some results that display the stoichiometry, or that's the relative percentage of what we call lithiation of a cell inside of an electrode. So what I'm looking at here is, to be precise, OCP, right? Different from the OCV I was talking about before. OCV is the open circuit voltage. I'm measuring it at the battery terminals. OCP is open circuit potential, a slightly different term. And we use that to talk about what is the voltage at a particular electrode. So I'll talk about a positive electrode, open circuit potential, and a negative electrode, open circuit potential. These potentials are combined in a subtractive way to give me the open circuit voltage, right? So if I subtract the negative positive from the positive, I'm going to get to the resultant open circuit voltage. Now, the problem with OCP, the trick here is OCP is not observable from the voltage, right? The open circuit voltage is a combination of two things that I don't know. And so this makes it tricky. We've been working on very clever ways here in our research program to sort out a negative and positive OCP when you do not have access to either. And some of it involves making some assumptions about what your electrode material is and what the fundamental characteristics are of the OCP curve of one, and then you can kind of deduce the other. I won't go into the details of that, but just suffice to say, knowing the OCP is very critical for correctly modeling a physics-based process. Capacity becomes a rather complicated attribute when you kind of dig in a little bit. We talked about it before. It's really the amount of charge, right, from 100% down to 0%. But we have different ways of sorting out capacity, because so when I hit 0 on the way down is 0 volt, or my 0 SOC is predicated on an open circuit voltage. But that's not a usable capacity, because if I'm pulling my battery voltage down, right, and I have some ohmic or polarization voltages, where the bottom of my voltage is different from the OCV. So I have to be mindful of carefully defining cell total capacity in that context. And the bottom part of this slide indicates that we can obtain an estimate of this, or a measure of the cell state of charge, directly from some of the electrochemical parameters. In particular, if we track the concentration of lithium that is in the positive and negative electrodes, and we compare that against the maximum allowable in those electrodes, we can use these equations to calculate directly the state of charge from the lithium concentration. All right. Parameter identification for physics-based cell models is probably the most difficult challenge that we take on. Because if you take the full physics-based model, and the industry has widely accepted the model that I've shown you, and that was originally put together by researchers Doyle, Fuller, and Newman. That model comprises 35 unique parameters that are indicated in the table over there on the right. There's a whole bunch in the negative electrode, a whole bunch in the positive electrode, and a whole bunch in the separator. 35 altogether. The problem with these is they are not a fully identifiable set, which means that some of those parameters are not observable from input-output experiments that we might do on the cell. Remember, we can only really measure current, voltage, and temperature. And somehow, with that and the knowledge of our physics-based model, we have to extract or suss out the values for all of those parameters. So because these are not fully identifiable, it's important for us to what we call lump the parameters, which is what we have subsequently done. So it turns out certain parameters appear in the model in groupings, and they're usually like an electrochemical parameter grouped with some spatial or length parameters. And those, when lumped together, can be identified. But unless we know some of the spatial parameters, we can't extract the underlying quantities, yet in most cases we don't have to. So it turns out if we do this lumping of the parameters, and that's what this slide is all about, the bottom line is I can reduce the parameter count from 35 all the way down to 24. And that set of 24 now lump parameters is fully identifiable. And we have means of extracting those from data. So the way we do this is using a very systematic method. We have designed here in-house a number of carefully designed laboratory tests that, again, using only input current, voltage at the terminals, and temperature, but in vastly different ways, we can extract subsets of those parameters by targeting specific tests to isolate or identify certain subsets of parameters. And if we perform the entire sequence of tests, we can put together the entire parameter set and thereby populate our physics-based model. And so that's the upshot here. Just to kind of walk quickly through these tests, one of the most interesting tests that we do is called EIS. And that's the one shown on the bottom. The one on the top is a pulse test. And I guess I'll quickly mention that. Here the idea is I'm going to take a battery cell and I'm going to introduce the largest current pulse I can over the shortest time. So that starts to look like a Dirac delta function in mathematics, although it's very hard to do in electronics and get it right. But if we do that and we think about it, we say, if I can make that pulse very strong and very short, in theory, I'm not going to excite any of the dynamic processes. And so I should be able to extract at least our R naught, right? Our ohmic resistance value very clearly. And so that's what's kind of shown here. And it turns out there's some dependency on the current strength with the change in voltage. And so it's not exactly a linear relationship, but you can kind of see that in the curve. And the one on the bottom is a test called electrochemical impedance spectroscopy, EIS, and that's just really a fancy name for frequency response. And yes, we do straightaway frequency response on battery cells. So we introduce sine waves of known frequency in, and we get sine waves of that frequency out, and we measure their amplitude and phase shift, but we can put together very interesting plots of frequency response. Now, we have to be very careful when we do EIS with a battery because a battery is inherently nonlinear. And so our expectation here is that if we keep our amplitudes very, very small, we'll excite only over the essentially linear behavior region of the battery. And in that case, the frequency response will make sense. And it turns out the frequency response conducted that way conveys a lot of good information, and we can extract a certain subset of parameters using that frequency response. So in the final part here, part 2, we talked about battery models. I kind of gave you I don't know, maybe a 20,000 foot overflight of some of the basics of battery modeling. Now I'm going to talk about some of the applications of those models to those BMS tasks that we talked about before. And this chart here kind of just recaptures some of the things I said before about the several functions that are executed by a BMS. And here we get into sort of the nits and grits and how it operates. So a battery application that is designed to manage the behavior or the performance of a battery pack really needs to know a couple of things. And it really boils down to energy. How much energy is stored in my battery pack right now? And how much power is available in the immediate future that my battery pack can deliver to the user? And so knowing energy, of course, is very important for anybody who drives an EV, because none of us want to run out of charge when we're driving down the highway. So I need to know with some great accuracy, how far can I go, or how much runtime do I have until I need to get to the next charger? Power is very important in other applications, such as hybrid electric vehicles. It tells me whether I can accelerate or accept braking charge, right? So I'm coming up on a hill. If I jam it on the accelerator, do I have available power over the next 10, 20 seconds, some power horizon future, in order to execute? But at the same time, if I'm doing regeneration, I need to know, is my battery capable? Is it in a state right now where it can accept a large surge of charge? So these are power limit questions that are also addressed by the BMS. And it turns out that neither the state of energy, the state of charge, or the state of power can be directly measured. There's no sensor that I can apply to my battery that's going to give me that number. And so I need to estimate things. And I need to estimate things based on things that I know, right? So energy can be calculated, of course, if all the cell total capacities and states of charge are known inside of a pack, right? I have to know what the capacity is, the true capacity, and I have to know what the states of charge are, and I can come up with an estimate of energy available. Power limits can be estimated if I know a lot more about my cell. I have to know all my states of charge, because I have to know if I have some headroom there, right, before I bottom out, for example. And I have to know my cell resistances, because those are going to throttle how quickly I can extract energy or insert energy into a battery. But none of those can be measured directly. And so I have to estimate those using the more primitive methods that we talked about before, focusing on SOC. So battery cell state of charge quantifies how much charge is stored that might be released to a load in order to accomplish a task, simply put. As mentioned, no sensor out there can measure SOC. Whether you like it or not, can't do it. We have to estimate it using basic measurements that we have: voltage, current, temperature. Unfortunately, it always boils down to those. And that's a pretty small subset of things that we have at our fingertips to use to make these rather sophisticated estimates. However, knowledge of SOC, which means accurate knowledge of SOC, is very important to calibrating a lot of my state of health interests, right? And I need to know that for state of energy as well as state of power. And so everything sort of cascades. We also, it's also extremely important to know SOC properly to avoid overcharging and undercharging my battery. These conditions are extremely dangerous for a lithium ion battery cell, right? Not so much for a lead acid battery, for example, right? They have their self-protective mechanisms that prevent anything bad from happening without a system to govern that. But in a lithium ion battery, you can get into big trouble in either of those conditions. So we have to estimate that, that status very, very carefully. And again, the cascaded effect of an accurate SOC estimate is going to impact the longevity of my battery cell, its immediate short-term performance, reliability, density, and eventually its economy. So SOC is a physical quantity that we can't measure, we have no sensor for it, but in theory, you could measure it, right? So in theory, if I could get right down into that electrode and I can sort of look inside the particles and count how much lithium is occupying the vacancies of my particle, the way a person occupies a room in a hotel, and I just count them up, then I can aggregate all of that information and have an absolute number of what my SOC is. But we don't have such insight into the battery at that level. It turns out that for the long-term health of the cell, it's never the case that we fill all the vacancies, nor do we ever empty all the sites. We never make it all the way full or all the way empty. So despite the fact that your phone says 0 or 100% on the charge, those vacancies are never all the way empty, never all the way full. There's always a margin of headroom there at both ends. And so the 0 and 100% are definitions that are based, I don't want to say arbitrarily, but they're based on certain established voltage limits within the cell. Okay, and there's some definitions that kind of fine-tune what we've been talking about with respect to capacity, and I won't go into those in too much detail here, but that's kind of a nice slide to study. And I'll wait for my slide to advance here. Some of these take longer than others. Maybe this one doesn't want to go at all. There we go. So how do we estimate SOC then, since I've made heavy weather out of not being able to measure it? Well, the way we do it is by actually leveraging the mathematical model of the cell that we know. So what I've shown here is sort of in the bottom right is sort of a notional method of estimation for SOC. I have on the left here kind of a taxonomy of estimation methods that we can discuss at some other time, just to give you a sense that there's a lot of people looking at a lot of different ways to do this. And to be honest with you, I review a lot of papers in this field, and if I see another paper from somebody telling me about another, handy dandy way to measure SOC, I think I'm going to scream. There's thousands, maybe tens of thousands of papers that keep rehashing ways to do this, and the fundamentals are already fixed, really, how we do this. And they've been fixed for about 20 years. And it's very nicely outlined by this diagram here. Here's my physical cell up in the top block. So that's the actual thing. Here's the actual battery current. I measure that current and I feed it into the model that I have produced of presumably that cell. I measure the actual response of that cell in terms of its voltage. I predict what the cell voltage would be through my model, and I compare them. If they are close together, if they are the same, then 0 is sitting on this comparator and nothing else happens. I have a perfect model. If they're not the same, then I introduce some kind of a feedback method to adjust the behavior of my model to look more like the actual thing. And so there are a number of ways to do this. One of the ways from control systems is called an observer. We can put a state observer in there that provides that feedback mechanism. Another generally more effective way is something called a Kalman filter. It's an optimal estimator. It's based on some stochastic principles that performs exactly like I'm showing in this high-level diagram to come up with this feedback method in a very special way to give you an optimal estimate of the cell voltage. We've been doing Kalman filter estimation of SOC now for over 20 years. And we have various flavors of it, but it is extremely effective at providing excellent estimates. And that goes for whether I'm using a equivalent circuit model or a physics-based model. People ask me all the time, what's better for SOC estimation? Well, if you have a really good equivalent circuit model, you can get SOCs just as accurate as a great physics-based model. So that, if that's your objective, then you can, retain the complex computational complexity of the equivalent circuit type of model and still get good accuracy on SOC. However, what you lose is all that other stuff, right? All those internal electrochemical processes that are so important for longevity. So here's the Kalman filter approach. I'm not going to teach a course here in Kalman filters. That's an entire semester, but basically what it does, it works on sort of a prediction correction mechanism, right? We have initialization of the algorithm. We predict the model state vector into the future one step. We predict something called the error covariance. So we have a statistical measure of how my error is propagating. And I predict my output from the state, right? In this case, the cell voltage. Then I compute my filter gain matrix. That's that feedback part. And then I estimate from my model with this gain matrix, the model state vector. We compute the estimation error covariance, right? So that's the prediction error, there's estimation error, and then we feed it all back and we go through the loop again. So what I'm showing you here are some Kalman filter examples. What I've illustrated is there's a charge depleting dynamic profile that's being executed here. And we're estimating the SOC in simulation by measuring, I think that's simulation, by measuring both the voltage and the current. And you can see you can't see the truth is lying underneath the estimate. It's almost dead on. And the lines you see around it are actually a very important aspect of this estimate. They are confidence bounds. So one of the nice things about a Kalman filter, because it's a statistically based estimator, it gives you confidence bounds in addition to your central estimate. So you can use the confidence bounds in order to put some safety and reliability into your BMS. So battery pack SOC can be measured in a similar way what I talked about with cell level SOC. There are some additional complications to measuring battery pack SOC, but the principles are exactly the same. Final thing I want to mention here is state of power. This is one that I find particularly interesting. And we'll start with just a general discussion on energy and power to ensure that we understand the difference here. Energy, right, the ability of the battery to do work. We normally measure the energy content of my battery in something called watt hours or kilowatt hours. And as mentioned earlier, it indicates the quantity of charge inside my battery. So available energy, like we talked about, is really equates to a fuel gauge, right? Are we full, are we empty, how far away? On the other hand, power indicates the manner in which that energy is taken out or added to the battery, right? It's the rate at which I extract that energy. Power, of course, equals the time rate of change of energy. And for an electrical system, power is computed as the product of voltage times current. And it describes the movement of charge into and out of the cells. So for example, if I talk about a high power cell, then I have a cell that can move charge at very high current rates in and out. And so you can see almost immediately that, gee, internal resistance is going to play a big role in my available power. So the industry likes to have nice, tidy measures of such things. So there's this measure that's emerged called the state of power. And it has a lot of different definitions, depending on who you read, but the basic fundamental definition is how much power on charge or discharge can I sustain over a specified time into the future? So in other words, what is the maximum power level if I establish a delta T into the future, say it's 10 seconds, and I want to draw a constant level of power, what can I do, right? And so, I like to equate this to, I cycle a lot myself. I'm in a spinning class, if you've ever done that, or edge cycling. And there's a power meter on the bike, right? It tells me how many watts I'm executing. And I'm always, I'm a power guy. I'm always dialed into the watts. And so one of the drills we do is how many watts can you sustain for the next 30-second drill? And of course, if I go out and I just hammer it and I hit 400 watts, well, that's going to last about 5 seconds. And then by, 20 seconds, I might be down to 150 watts. But if I start out at like 200 watts, I can hold that for maybe 20 seconds or 30 seconds, right? So you kind of think of it in those terms, how your battery must function. And so this term state of power, you'll see it is power limits, state of available power, peak power. And it's almost always used in the predictive sense, right? So I want to supply an upcoming load demand, right? I want to accelerate, need to climb a big hill, or on the other side, I want to supply a surge of charge for regen braking. So I have to inform the vehicle controller what it can safely expect from the battery. So estimation methods cover the gamut. We can use equivalent circuit methods in terms of model-based approaches, and it relies on these simple models. And I basically calculate what's the max, voltage, what's the max power that doesn't exceed certain established voltage and current limits given this simplified model of the battery. If I want to get deeper into what I call a more realistic answer of state of power, I need to dive into the physics-based model, because there I can explore what are the real limits, what are the real things that are holding me back from exerting more power. And so there I may see, I've got limits on the concentration of lithium. It can't go below a certain level. I have limits on the overpotential of my electrode. It can't drop below a certain level. And if I put those electrochemical limits in place, and then I try to extract maximum energy at a maximum rate, I'm going to get a different shaped curve. So we have both equivalent circuit or empirical methods, as well as the physics-based methods on which to base that calculation. This is one very popular sort of standard way to characterize a state of power. It's called the HPPC, the hybrid pulse power characterization. And it basically introduces a series of pulses. It measures the current, the voltage, the delta T, and you do some calculations based on current and voltage limits, and you come up with these sort of estimates, these kind of rough estimates of available power. A new approach that we've introduced is based on a control method, actually, a predictive control method that seems well suited to this, because after all, we're looking out into the future. It's called model predictive control. I'm not going to talk about that, but it turns out that MPC is a nice way to put together an optimized current profile, or an optimized input profile that respects constraints in real time. That's really the upshot. And by doing so, we can allow some dynamic movement in the instantaneous power, and that is not assumed by the standard approach. And so we can remove a little bit of the conservatism by doing some calculations based on a more dynamic calculation. All right, so coming to a summary. So BMSs, BMSs rely heavily on the underlying mathematical model that describes the battery cell. We can describe that model using either empirical equivalent circuit methods or the more complex physics-based methods of models for our monitoring and control applications. State of the art right now, largely using ECMs, but we believe PBMs unlock the possibility of extending life and improving battery pack performance, and that's been shown by tremendous interest that we're getting here at our end from a lot of industry partners who are looking to move ahead to the next level. Of course, the ECMs represent cell behavior using analogs of cell behavior built from simple circuit elements and simple structures. PBMs use the first principles of mathematical equations of electrochemistry, but they can be really complicated to implement. So one of our key research thrusts here is how to develop computationally compact versions of the physics-based model that are, and this is the holy grail, right? No more complex to calculate than an ECM, but they retain all of the information richness of the PBM that we can use in order to affect advanced control strategies. So that brings me, wow, right down to the end of an hour here. And I'll just leave you on this. My colleague Greg and I have been working in this field a long time. Greg put out 2 books over the last few years. The first 2 volumes in the battery modeling and equivalent circuit methods of the battery management system series from Architect House. And he and I co-authored the 3rd volume, the red one there on the right, and that was just published in January. And that is focused on all of the latest and greatest physics-based methods of battery management technology. And so those are out there and available. You can also find full semester-long graduate course PDF notes on a lot of what I talked about today. There's lecture videos, ECMs and PBMs at the sites that are indicated here. And there's another semester-long grad course PDF notes on the 2nd book there at the bottom on that link. And I put at the end of this some papers, some of them mostly by us and our researchers, also by other folks, if you want to delve into some of these topics in more detail. And with that, I will conclude and happily take any questions. I think I left some ample time, hopefully, for some discussion.
Great, great presentation, Scott. Thank you so very much.
Drinking from a fire hose.
All right, let's have some discussion. Questions, thoughts? Batteries, battery management systems?
Yeah, thoughts, perspectives?
Yeah, Professor, I have a question.
Yeah.
So the background of this question is that I have an old iPhone that will go from 20% to 1% in about 10 minutes, and then it'll stay at 1% for hours. And so my question is, I don't know why that is, but my question is, do estimates of the state of charge of a battery assume a certain state of health, or in other words, as the state of health of a battery gets worse, then do the state of charge models become less and less accurate, or is the state of health maybe used as an input for the state of charge value?
What a great question. What's happening with your phone sounds like something that was that happened to my previous my Apple MacBook Pro, where I would charge it to 100%, and it would fairly readily go down to 50%, and then from 50%, I had about 5 minutes left before it was dead. So it was kind of a different, manifestation of the same disease, which is really, those estimates are not correct any longer, right? Those estimates are completely corrupted by the actual behavior of your cell. So what happened to your battery cell over the life, different things are happening. There are a lot of different aging mechanisms that affect the performance of your battery cell. One of the most pernicious is one called lithium plating. And that's very hard to avoid. And what happens is, the way the battery works, these ions are shifting back and forth across the electrodes through a process we call intercalation, and it's migrating into those vacancies in the electrodes. But what happens with lithium plating, the resistance of the ions trying to intercalate into the electrode is so high that they can't all make it. And so the ones that get sort of left on the surface end up in a separate side reaction, and they get rendered into lithium metal, and they actually plate on the surface of the electrode. And that has 2 very bad consequences. One, there's less lithium ion fewer lithium ions now to shuttle the charge back and forth. And number two, it's sealing up some of those entry points for future ions to intercalate. And so that's probably the biggest factor of degradation that affects our battery. So when your cell phone, you get it's new and it lasts seemingly forever, and then after a while, a couple of years, you realize, hey, the more common thing is it lasts a certain amount of time, and then boy, it drops off a cliff, just like my laptop did. And that's lithium. That's a lithium plating effect. But there's other things going on. You have loss of active material. Your electrodes eventually break down, and the hotel rooms are collapsing, and there's no place else for these ions to shuttle to. And then there's other things. Your electrolyte can degrade and so forth. So what happens? So what you're describing is a change in the battery's state of health that is changing the snapshot of what that battery model needs to be for the estimation algorithm that was implanted in that phone initially. So now that estimation algorithm is working with it's a very inaccurate representation of the actual model. So what you're getting out of it is completely garbage at that point. Now, the holy grail here is kind of what you suggested is there a way we can track the progress of these degradation mechanisms and dynamically adapt the model that's embedded in my management system so that it can keep up with the current state? And that's not done right now. That's not done, with any fidelity right now. And there are people doing different things with machine learning techniques and things like that to try to empirically follow the trends of what the battery is doing. But there's really nothing that's in a real accurate physics-based way figuring out what's the mode of degradation here, how can I adapt the model and then recalculate my estimates based on a more accurate picture. And that's at the forefront of research right now, to be honest.
Very, very interesting. Thank you for the response. I wasn't just asking so that I could figure out what was wrong with my phone. By the way, I was interested in the ideas behind it. But so this lithium plating and collapsing of hotel rooms and things like you were saying, is that something that is a symptom of batteries that are not meant to be quite so long lasting, like a phone battery, or is that symptomatic of all batteries, including EV cells, or is there a way to mitigate things like that if you make a higher quality battery, like maybe an EV cell would be expected to be?
Yeah, another really, really good question. Wow, you're asking terrific questions. So there's two sides to that answer, and one is yes, there is a rather substantial push in material science research right now to see how we can better design the electrode, crystalline structures and embed different types of materials to be more resilient to the types of effects that I described. And there's different compounds in the electrolytes, and that's an entire electrochemist, material scientist kind of question to answer. Now, we look here at the question from another point of view. We say that if you give me the cell as it is, a pristine cell, we would like to understand exactly what the causative effects are, or the causative influences are on those degradation effects. So for example, lithium plating, good example. We know from our electrochemistry friends that lithium plating is most prevalent at certain operating ends of the operating regime. So for example, very low state of charge, very cold temperatures, and then very high charge rates. If all of those come into confluence, you are going to induce lithium plating almost instantly. In fact, we had a situation here, we had a new cell, it's a pretty expensive cell. We had some students who were doing some research on it, and they had it in a thermal chamber at like minus 15 C, and they put some massive current charge cycles into it, and the battery was dead in about 10 cycles. And they couldn't figure out why. Well, they lithium plated it almost entirely and almost instantly. So we know that those conditions bring about a drop in the what we call the side reaction over potential. There's an over potential level that exists at the surface of the electrode. That's where it's throughout the electrode particles, but at the surface it's most apparent. And if that potential drops below zero, actually a little bit above zero, but let's say it drops below zero, that induces the side reaction that instantly brings about lithium plating. And so our conjecture is, okay, if we can use an accurate physics-based model and our estimation techniques can track that side reaction over potential, then it doesn't matter if I'm in the cold weather and I'm attempting to charge fast. If my battery management system says, whoa, your side reaction over potential is dipping down towards zero, it can affect an immediate backing off of the current. And by doing so, it avoids the bad place, right? It completely avoids the occurrence of lithium plating. And so our strategy is to understand these mechanisms, understand the causative influences on them, and then build clever control strategies that prevent us from entering those harmful regions.
Right, I see. Very interesting. Thank you very much. Wonderful, wonderful lecture, and thanks for the answers to the questions.
Can I ask a follow-up question related to that?
Yeah.
So what you were just mentioning about the cold and the charging fast, is that why current EVs, a lot of them require like a warming up process in the cold weather before it allows you to like use a DC fast charger?
Absolutely. Yeah. So charging is more effective and efficient and safe when done in a heated state of the battery, when the battery's at a warm temperature. So I don't know what you drive. I drive a Tesla Model 3, right? So if I have my Model 3 parked outside and on a cold morning, and when I'm driving into work, there's a little indicator on the screen that tells me, it's basically a bar. And when I'm regen charging, that green bar moves to the left to show me the extent of charge that I'm putting into the battery at that moment. On a very cold morning, the available swath of that green bar shrinks proportionally. So it's a very cold morning. I've seen that green bar, the potential length of that green bar go to about zero. So it says, I'm not going to allow you to regen charge at all until I bring your battery up to a safe temperature. So I have to drive for about 10 or 12 minutes before the green bar begins to grow again. It says, okay, now I'm finally warm enough. Well, I'll allow you to inject charge into the battery without causing harm. And so that's done for exactly the reasons I'm describing.
Okay, thanks. I guess one more question. What does the actual battery management system look like? Like, for instance, I would assume you need a voltage sensors, current sensors for the battery, a microcontroller to manage the control systems, some balancing circuits on each cell. Is that basically what it looks like?
Yeah, all of that. It's usually not on each cell. A battery management system is usually on current car self-contained. The sensors may be, at least temperature sensors and some voltage sensors on each cell. But usually we're not controlling most modern cars at the cell level, although there's a lot of advantages you can get by doing that. Most battery management systems are those distributed sensors, but more of a consolidated set of hardware that does the processing.
Okay, good to know. Thanks.
I have a question. This is a very interesting presentation, Scott. As you described, the voltage is actually dependent on the state of charge. So, at what kind of voltage would be considered as a 0%? I mean, what is the voltage at 0% of state of charge divided by the voltage at the full state of charge? What is that ratio?
Okay. But to give you an example, so that the actual numbers depend on the chemistry of the cell. So when I talk about the different chemistries, there's some cells that have an iron phosphate cathode. NMC, I mentioned nickel, manganese, cobalt cathode, and there's lithium, titanium oxide, LTO. There's different chemistries. They have different voltages, but essentially they're in the same general range. And to give you an idea, the bottom range of voltage that would give you 0% SOC would be between usually 2 and 2.5 volts. The nominal voltage would be maybe about 3.6 volts. The high end or 100% voltage would typically be between 4.2 volts, right in those ranges. And
I see.
that's at the cell level, yeah.
I see. All right. Thank you.
So yeah, you never drive your battery voltage down to zero. It never gets close. I mean, that would destroy your battery cell. There's a lot of bad things that happen there. And obviously overcharging, it has its own issues, and the least, not the least of which is fire and explosion if it happens.
Yeah, thanks.
Scott, any follow-up comments? Now you got us all thinking about fires and explosions.
Well, I hope you're not.
The role,
Fires
thoughts
and-
on the role of the BMS system to ensure that doesn't happen?
Yeah, we're working on it. Yeah, if we do any fires and explosions, we want to use the blast lab. So not our own lab. So we're not configured for that. But that is some of the fun testing that people do with these things, right? To push them to their design limits and so forth. Of course, we can't do that here. And for that reason, we do a lot in simulation, as you can see. A lot of the numerical experiments we do with these various models to test their efficacy, obviously, ultimately on the battery cell. But the problem with that is that the actual battery cell, if I have a model that's physics-based and I'm trying to validate whether or not my concentrations of lithium on my reduced order physics-based model are correct, I have no means to do that inside of a real cell. There's no sensor, no insight into that. So just as a point of maybe curiosity, the way we do that is we have what we call our full order model. We use in our case, COMSOL multiphysics, a very big finite element package. And we have the full blown Doyle-Fuller-Newman model, which, by the way, we've extended with some other features to add some greater accuracy to it. And we run that with incredible fidelity. And so that gives us what we call our ground truth baseline for what is really happening inside of a cell. And then a lot of our research, since we're engineers, we're looking for engineering applications of this research. The full order model, might run overnight or whatever on a high-end computing device, is not implantable in a BMS. So we have designed various techniques to take the information content of that model and, like I said before, crunch it down, make a computationally compact version of it that still retains a lot of its information richness. But how do we know that crunched down model is representative of anything reasonable? Well, we can compare it against our full order COMSOL model, and we can check our estimates of the internal variables with the reduced model against the full order thing. Of course, the input output and maybe the thermal characteristics we can do on the actual cell. We can measure the voltage, we can measure the temperatures and so forth that way. But we do have to rely on some very accurate high-end full order models in order to validate a lot of these techniques that I'm talking about here. And that's a very fun part of the job here too. I didn't get a chance to talk a lot about the control end of things where I work, but there's a lot of cool stuff we're doing over there too. I touched on it a little bit with the state of power estimation. We've come up with some very clever schemes there that capitalize on the physics-based, the reduced order physics-based models. But another aspect that I didn't talk about at all was fast charge. We have done quite a bit of work in generating highly effective fast charge profiles that mitigate a lot of these mechanisms of degradation and loss of performance that we can model. And these we've validated to some extent in experiments as well as obviously in full simulation. And so a lot of that fast charge work is, kind of front and center of what we're doing here with the Aspire program as well. But there's a wealth of resources out there. I'll also mention one other thing, since you're here. My students have been working here on the Aspire project in particular, have been putting together a toolbox of all of these functions, all of the equivalent circuit model things that you've seen. We have a reduced order physics-based model called a single particle model, and some other toolbox utilities that do the simulation and so forth for battery analysis. Everything that is in that regard has been uploaded to a toolbox that is in the I think it's in the box structure somewhere. I should have had a slide with that address on there. But over the course of the last year, we've been uploading and fine tuning, and all of that is sort of production ready. And we encourage any and all users of Aspire to avail themselves of those toolbox functions. If you have any need for battery models in anything you do, in any simulations, any hardware in the loop or anything like that, and you want a battery integrated or a battery pack integrated into some of that, please turn to us and we'll guide you through that. We're happy to schedule meetings and get you off the ground and running with those toolbox functions.
Very good. Well, we promised leading expert in the space. I think we delivered.
Thank you. I really enjoyed it. Thank you all for attending. I'm very appreciative. And great questions. Great questions.
All right. If there are additional follow-ups, Scott, we'll collect them and may link you in on Twist to help with some of those answers. And if you can send me a PDF of the presentation, I'll get that access for all the
I'll send you
students.
the entire presentation, and any other info you guys want, just ping me.
Great. Thank you. Thanks,
All right.
everybody.
Thank
We'll
you
see
all.
you.
Bye.
Thanks.